Network routing has hit a physical limit. Hardware clock speeds simply cannot push data beyond 1.2 terabits per second. The standard TCP/IP architecture routes information across a two-dimensional grid. Every piece of data travels along strict linear X and Y axes, moving step by step from one centralized node to the next. Because these pathways are entirely flat, vectors inevitably cross. When massive amounts of traffic intersect up in centralized hubs, the resulting bottleneck creates what mathematicians call a quantum information merge conflict. The system literally chokes on its own intersections. Engineers realize they cannot engineer their way out of this with faster processors. To push past the terabit threshold, they have to abandon the rigid, two-dimensional Euclidean plane of standard printed circuit boards. Every two-dimensional network eventually chokes on its own intersections because flatline geometry offers no path for two signals to occupy the same space without collision. On a traditional one-dimensional number line, prime numbers appear as a chaotic, unpredictable sequence. But when folded into a polar quadrant map, graphing primes as reciprocal gaps and rotational vectors, a structured geometry emerges, a dense central disk surrounded by sparse outer rings. Here, prime numbers behave like harmonic wave emissions. They radiate outward in a predictable pattern, acting as a precise coordinate system rather than isolated dots. The empty spaces, the prime deserts, are mapped mathematically as orthogonal 90-degree normal field vectors. They provide the directional force that structures the physical space. This hidden geometric structure provides the rotational vectors and coordinate stability needed to lift the entire network into a higher dimensional manifold. At the core of this manifold is the topological fold identity, the mathematical anchor that allows those rotational coordinates to exist without signal drift. This animation shows the equation e to the I pi plus pi to the 0 equals 0 to the 0. It acts as an active singularity, where observer and action fold perfectly, allowing complex data streams to wrap seamlessly into a curved manifold without loss. This approach mirrors the space-time topology proposed by Kurt Gödel in 1949, outlining exact mathematical solutions to Einstein's field equations, describing a rotating, multidimensional universe. By applying that level of physical mathematics to data transfer, the network evolves from a static flat map into a path-independent routing manifold. The route adapts to the information it carries. To utilize this space, the network structure unravels from a standard 3D sphere and projects into a four-dimensional hypersphere torus, called the Hopf fibration. The math breaks the structure down uniquely, compressing a three-dimensional sphere into a two-dimensional base surface, then enveloped entirely by one-dimensional circular fibers. Inside this four-dimensional coordinate system, a data packet doesn't travel in a straight line. It mathematically rotates towards its destination along the shortest geometric arc. This 3D visualizer tracks an active query moving through the R4 prime router. The white pulse path shows the signal sliding effortlessly along those interlocking circular fibers, bypassing centralized hubs entirely. By folding the network into a 4D torus, data packets find unobstructed parallel pathways, eliminating the mathematical congestion of the two-dimensional plane. Hardware requires a physical addressing layer to navigate this torus. The R4 utilizes a discrete architecture known as the hex-hive modulo 6 topology. This visualization reveals a hexagonal grid where parallel phase transport channels curve past each other, locked to distinct prime coordinates. Tightly clustered primes act as low-curvature switching anchors, forming stable structural junctions that allow data to hop seamlessly across parallel channels. As the signal makes these jumps, its phase shift is calculated using the Berry connection, measuring the exact physical curvature or mathematical friction of the route. Because these prime anchor paths are guaranteed never to intersect naturally, the system executes completely collision-free routing, retrieving complex data contexts in less than a millisecond. Curious, Tone. Look closely at how the math behaves. The R4's information density flows in waves across physical substrates, mimicking the behavior of quantum mechanics. The event trace table of this routing engine maps perfectly onto the Riemann zeta function, a famous mathematical framework detailing the distribution of primes. In this engine, primes represent the visible mode structure of a deep, recursive radial partition, the harmonic frequencies of the space itself. To steer packets through this environment, the system relies on a coupled field equation. This formula actively balances the physical graph connection between nodes against the continuous mathematical curve of the hyperbolic space. Rather than exhausting computational power calculating a path node by node, the router emits a harmonic wave and lets the natural geometry of the prime sequence predict the fastest possible route. Even in this elegant system, signals inside the discrete phase space occasionally overlap and create destructive interference. But instead of dropping this as processing noise, the dense collisions cancel out at the mathematical origin point. They form quantum nulls and are preserved as condensed topological memory. Compare that graceful resolution to legacy linear computing, which scaled by building increasingly massive physical footprints to brute force through parameter bloat and traffic jams. True sub-millisecond processing speed is not achieved by forcing more data down a flat linear pipe. It requires aligning our physical hardware with the harmonic topological geometry of the universe itself.